Greetings and welcome back to the Neural Network Arena where we're leveling up our machine learning one feature at a time. In today's episode, we're doubling down on complexity by adding a second input to our model. I'm your host, Simpleton, here to keep it simple with the Simpletron. Imagine you were juggling one ball versus two. Keeping it simple has allowed us to easily and clearly see how every detail affects accuracy. But to see the impact of some new features like loss functions, activation functions, and feature scaling, we're going to need two inputs to see the impact. The example we will use today is predicting income from years of experience and years of college. In today's showdown, we got a three-way face-off. In the left corner, we are going back to our Simpletron, the Blackbird. It will continue to have a single input. In the right corner, we have Hayabusa, our champion from previous models, which we will upgrade to handle two inputs. And in the center, we've got the infamous GBS, aka gradient descent. Sure, it's rocking parallel processing and dynamic input handling. Too bad it also brings all the BS of GBS. The Blackbird is following our basic neural network loop. Let's use predicting house value from square feet as an example. Step 1, predict. Take the input, square feet, multiply by the weight, and then add the bias. Now, the weight and bias can start with any value in this model, but note, often in practice, they start weights and biases with random numbers. I don't really love that. I feel like once we get this model right, you should be able to start them at any value, and the training process will keep adjusting them until they get to the optimum values. 2, check the prediction. Compare what we predicted against the actual value, also known as the target. And how far off that is called the error. Step 3, adjust. Tweak the weight and bias based on the size of that error. But now we have a second input, which means our neuron isn't just working harder, it's working smarter. There's only three small changes to make this work. We need to, number one, have two weights. The parent class takes care of that, so if there's two inputs, we'll automatically have two weights in the model. Number two, make a prediction. So where before we had the input times the weight plus the bias, now we've got the input times the weight plus the other input times the other weight plus the bias. So we're just putting in that new input times the new weight. And then third, we need to obviously adjust that weight after we check our error. Here's a diagram the way those mathematicians like to look at this. So if you take a look here, this is actually for any number of weights. It shows 1, 2, and 3 as an example, but then this and means it could go to whatever you have. You know, a lot of time with image recognition, they give you one for each pixel, so it could be in the thousands. But no matter how many you add, it all works the same. You take an input times the weight, and then sum all of those up, add in the bias. Usually they'll run it through an activation function, and then that gives you Y, the output. So here's the plan how we'll get that done. Number one, we're going to test our existing single input Blackbird and make sure that it still works. Number two, we're going to copy it and add the second input. That'll be the Hayabusa. And then third, we'll throw the GBS in the mix, which is already an existing model that we're really not going to ever change because that's kind of our benchmark that we're going to compare our experiments against. Let's look at the details of how we're going to update the Blackbird copy into the Hayabusa. First, we're going to have to capture both inputs. And then as mentioned, the parent class already will give us a second weight. Since there's two inputs, there will be two weights available for us to use. Third, we're going to update that prediction logic by putting in the second weight times the second input. And last, we'll update the adjustment to update our new weight. We cleaned up the organization of this source folder quite a bit. So now you can see we really only got these three folders. We had all these files before for the engine, they're just kind of out here. Now they're all in this engine folder, which really makes it nice and clean. We still got the arena settings out here where we control everything that's running. We want to take that out. You can see also the subfolders we did. So like for the gladiators, for example, it used to be all the gladiators were stuck in this one folder. Then afterwards, I would move them out and try and keep it organized. It was a mess. So now, put in as many subfolders as we want, and the engine will search for it. What I'll probably do is after the episode's over, I'll rename this Blackbird 005 or something of that nature, so that then we can, when we're doing 6, do it again and not have a conflict in those names. And also, let's take a quick look at our training data. So you can see in the arena settings file, we have it's still called the training pit. We're kind of in the process of switching this name over to just arena, but it is the predict income to inputs. And just like with the gladiators, we added subfolders, like we have the subfolders for the gladiators, we also added subfolders for the arenas. So wherever this is, anywhere within this, it'll find it, and that just allows us to keep things more organized. Again, I'm going to have an episode 5 folder for this one, and you can see here predict income to inputs is right here. So let's take a look at how exactly we are generating this test data. So it's pretty straightforward. As with all arenas, we pass in the number of samples that we want. And for each sample, it will first generate a number of years of experience and number of years of college. Experience anywhere from 0 to 40 and college anywhere from 0 to 80. Then the way it determines the salary takes a base salary of 20,000, and for each year of experience, it gives you 3,000 on top of that. For each year of college, 2,000. Now note, that's not exactly lifelike, but the purpose here is to build some linear data that we can use to test two inputs on the neural network. There's also an option for noise. Right now, the noise is off because what I ended up discovering in this episode that was pretty cool, and it mentions it up in the comments here. The uh, the bias of the neuron will come out to this almost exactly, and then each of our two weights will come out to this almost exactly. So it's pretty cool seeing how the neural network actually goes in and just from this data is able to come back and show us the numbers that we put in here. And if you change them, then the neural network finds the new ones. And here is the actual calculation. So again, that's the base salary plus the coefficient of experience times the years of experience, and the coefficient for college times the years of college plus the noise. And then it just puts them all on a list and sends it back. So that's how we're generating this training data. Let's get on to the fun part of messing around with these models and getting this second input in there. We're going to run it once, like we said, make sure it works. It wasn't that accurate. A lot of absolute error, mean absolute error. So that's the average per prediction. So that's quite a far. We're $17,000 off, but that's because it's only factoring in one input. So this right here, this bottom line here is the training data, and this is quite a long. You can see it goes way out a long list of lists. So inside of this outside list, there is a list of three numbers, and it's three numbers all the way through. Each one of those is one of our training samples. The first number is the years of experience. The second number is the years of college, and the final number is the income. So we will train it with this and then try and make our predictions. When we did that a second ago with the Blackbird, only looking at one of the inputs, it wasn't able to get that great of a score, was it? So let's take a look at how the Blackbird is doing this though. One thing that's nice when we cleared up a lot of the boilerplate, our model is pretty concise now, not a whole lot to it. And the best part about that is all you really have here. So this is still boilerplate I can't get rid of. This is the constructor, but it never changes. This is really the heart of the model, what makes the Blackbird the Blackbird. As we're looking at, let me pull this back up a little bit so that we can see our training data as we're doing this. So this gets called for each one of these lists of three. This gets called, these three numbers are passed in as training data. So the input is the zero element or 20 years of experience. As mentioned, the Blackbird isn't factoring in the years of college. And then the target, we could put 2, or which would be 0, 1, 2. What's even better, we put -1, and that just means always use the last one. The reason that's nice is because that way this target line doesn't have to change when we go from 1 to 2 to 3 to 4 different inputs. Instead of changing this every time, we just say, hey, the target is always at the end. Now, as we mentioned earlier, Blackbird's just doing our standard neural network training loop. Step 1, predict. We do that by taking the input, which is this number here, 20 years of experience, times the weights. It starts out by default at 0 and then adds the bias, also 0. So the very first prediction of the very first sample should be 0, right? Then it takes that and checks that against the actual target or the third number. It says how far off are we? That's the error. In the beginning, the error is usually quite large. It takes that error and then it updates the weight, doing error times learning rate times the input. And by the way, this is where I think GBS first goes off the rails, is that multiplying it by the input is not, just does not seem right. I haven't found a better way, so I can't gripe too much, but I'm sure it's out there. The bias you can see is similar to how the weight's updated. It's just it doesn't have the input. Now the problem with just taking the input off is if we do that, then these two are updating by the exact same amount each time, and they will stay the exact same distance away from each other. Or in this case, if they both started out 0, they would always have the exact same value. And that doesn't work either. So we need something here. I just don't think it's input. In any case, after that, we just have to return back the prediction for reporting purposes, and it's all good. We updated the model's parameters, and we return the prediction. Done deal. So let's take this and now update it to do 2 inputs. We're going to paste this in, and we're going to call it Hayabusa. All right. That's the Suzuki Hayabusa. Uh, this version will utilize both weights. Remember, in the Blackbird, even though we were given both years of experience and years of college, we only were looking at the years of experience, and that's part of the reason why this accuracy stinks. So now that we're down here with the Hayabusa, we're going to have an input. We got an input. Let's rename this input 1. You know what? To make everything fit a little better, we're going to just go INP1. And then let's do the same thing for our second input, but we'll make that 2. And as a 0 base, that all right. So now when we're looking at this, 19 will go into input 1. 1.7 will go into input 2. Then when it runs the next sample, 31 to 1, 3 to goes to 2. And the target remains unchanged. So now when we make our prediction, though, we have to include both lines. So we're going to say the input, that would actually be now input 1, oops, which goes with the first weight. You know what? I think it'd be a little bit more clear to just keep these numbers the same. We'll name this input 0 and input 1 because these we control. This starts at there. So now, but that way it makes it a little more, it goes together a little bit better. So input 0, and then, so this is the input 1 times weight 1 plus the bias. Now all we need to do is additionally add, you know what, let's put that right here, add input 1 times, I guess I could have copied that, huh? This. Now, since it's just adding these 3 things together, the first weight times the first input, the second weight times the second input, and the bias, we can add them in any order. And that is now our guess. But it doesn't like that, huh? Maybe I have to put the plus up here. Maybe I have to put it all on one line. Thought I could move that to multiple lines. Not sure why it's not letting me. Okay, but in any case, there it is. Now, the error, that remains unchanged, right? It's the, let's just look at our plan here. But so second weight, we included it in our prediction, and now we need to the last thing we need to do is update the weight. So the error doesn't change. The way that this calculates, doesn't change. We just need to do this twice. So now we'll say input, our weight 1 rather, equals error times, and instead of input being just like this, we need to go input 0 to make that the first input, and input 1 to make it the second input. Okay, and that's that. And return the prediction. I think that's all there is to it. That's pretty simple and straightforward, isn't it? Let's see if it works. So we'll go down to our arena settings. We will add the Hayabusa, and we will cross our fingers. Let's see what happens. Well, looks like they both ran. And look at that. Factoring in the second weight, we got it perfect. Now note, that's partially because we aren't including any noise. All right, let's throw GBS in the mix now. Now, let's take a look at that first. Our GBS model here is a little bit different in how it works. Instead of having a separate variable like we did in Hayabusa, we have one input variable for the input 1 and one for input 2. I guess I should probably just call them 0 and 1, huh? But in GBS, it just has a single inputs, which has got both of them in it. And that's what this colon -1 means, is take everything except for the last one and put it into inputs. Then when it does the prediction, you'll notice in our Hayabusa, we had both pieces there, right? We had input 0 times the weight and times bias, plus input 1 times the weight, and then that's it. But in GBS, instead of having each input separately, it does for the prediction, and it does this np dot inputs, comma self dot weights plus the bias. So what this does here is it multiplies all the inputs times all the weights and then sums them up. And it does this in a very efficient way as well. So if you it does this in a way that really utilizes your 3D graphics card to do these calculations in parallel so that it can save a lot of time. The error calculation remains unchanged. That's just how far off is our target from our prediction. But the weights, you'll notice, is a little different too. Again, when we were looking at Blackbird, we had, not Blackbird, Hayabusa. When we were looking at Hayabusa, we had each weight updating individually here. But in GBS, it again accomplishes that all in one line. So this formula here, self dot weights, uh, takes all the errors times all the inputs. And again, it correlates those. So the first weight goes with the first input, the second weight goes with the second input. But with one line, it's doing what we did by hand in the Hayabusa. If we had 10 inputs, we'd have 10 lines doing that. So this is nice, concise. And again, this is more performant than the way we're doing it in the Hayabusa. It does them in parallel and utilizing the 3D graphics technology better. But the question is, what about the results? Let's see what we see here. Oops, I guess I forgot to add GBS. Put the GBS in and run it again. Now all this code stuff you see flying by, that's just the epoch summary for each one of these. You'll notice while the Blackbird is suffering, the Hayabusa and GBS are both perfectly correct. So not only that, you'll notice they each are behaving identical. So not only do they have the exact same number right, they have total error identical. So of course MAE also identical, but even the final weight identical, and the number of epochs to converge. Uh, Interesting that the GBS actually took longer to run because those methods are supposed to be more performant, but I think it's pretty safe to say that that's probably because of something else going on external to this. The GBS should run faster, so maybe it was, who knows with the multitasking going on a PC like this. In any case, the point being, these two models behave identically, but we have a difference in how we build them. Now, what's the purpose of that? When you're doing it all like this, it's a little bit not as good to tinker with, right? But it will give us a good baseline. The Hayabusa, where we've got it broken out line by line, is this place where we can tinker and mess around and try and figure out exactly how to beat the pants off GBS. And then we can run them and make sure that we don't, for example, get worse than the GBS. Let me share something really cool I realized while we were doing the two weights. So you look at this data generation algorithm, and it uses these numbers 18,000, 12, and 8 to generate the training data, that looks like, you know, this. But the neural network then takes all of this data and actually backs into these numbers, never having received these numbers, only having received the data. So, for example, look, we could change this to 14. And let's go and change it. We're only going to have to run one here. So let's take the Blackbird out and GBS out. And as a matter of fact, let's run it like that. So when we run this, you'll notice we change the data here. 14,000, find the bias ends up 14,000. This coefficient 12,000, 12,006, 8,000, 80, 30. Whatever we set these to, we could change this to 22, this to 2, this to 24, run it again. It's going to find those underlying numbers. It never gets these numbers. It only gets this data. This guy had 14 years of experience, 4 years of college, and he was getting paid 348,000. That's a good darn job, right? But despite never receiving these, this is what it finds. And what makes that so powerful is that in the real world, we don't have numbers like this that tell us this information, but the neural network can figure out what these underlying numbers really are in the real world. Let's take a look at it with the graph. So let's run this one more time. And again, we're going to get 24, 12. So you can see here, now this graph has got 4 different axes for each of our elements here. So our bias here, you can see started at 0 and it goes up to this right here is the bias, so to 24,000 about. The orange line, that's the weight 2, comes down to 2,000, just like we have it set here. The blue line is the weight 1, 22,000. So that thing in the very beginning jumped up there and then dropped the whole way. And this line here is the error. You can see the error just keeps getting slightly smaller and smaller and smaller. This is a really key point, so I wanted to just do a slide on it. The data generation parameters like this, years of college, years of experience, and base salary, the neural network never gets those. It only gets the resulting data. And then the training process learns what those parameters are. After it's done training, the weights and the bias is going to equal these values here. And that's the power of neural networks, because in the real world, these aren't set by some numbers we put in. These are set by what actually happens, and the neural network is able to go in and figure out what those underlying causes are, and then it makes good predictions. One thing to be wary of is if you have big differences in the size of your parameters. One thing that can happen is you can get what's called exploding gradients. The weight updates keep growing. Actually, it kind of toggles. It goes from a large positive to a negative, like 20,000 positive, negative 30, 40,000 positive, negative 50, but exponentially up. So it keeps bouncing back and forth until eventually it gets so huge that you can't even sort in a floating point, which is a ginormous, unimaginable number. But that happens when sometimes when the weights are greatly different magnitudes. The other thing is the large weight is going to dominate the updates compared to the small weight. Let's take a look at our model to see why that is. So if we look here, here's the Hayabusa model, And you can see the formula to update the weights. It's error, which is going to be the same for both of them, and learning rate, which is the same. But if this input is really small and this input is really big, this update's going to have a lot more effect than this one will. Then another thing that can happen is you can run into floating point precision problems where you don't have enough precision to capture the change and it just kind of gets stuck on a number and you end up seeing like all zeros at the end of your numbers. And then the last thing is it can overfit to the large input, meaning it works good on the training data, but when you get out and do new data, it's overfit to that training data and it doesn't adapt well to the new information. Now, this here was some AI art that I thought was just kind of funny, so that's why I included it. It does make some pretty good pictures, but it sure can't spell worth a darn, can it? In any case, let's talk about the key takeaways from what we covered today. So, real world applications need multiple inputs. No problem. We just create a weight for each input. The same simple prediction and update applies. We just sum them up, and that is the prediction. Next, neural networks learn the underlying parameters. We have actual numbers in the parameters so we can create the data, but in the real world, that's not what happens. But the neural network figures out what they really are, and then it's able to make good predictions after that. And finally, inputs of different sizes can cause problems like exploding gradient and domination. So that'll lead into our next video, which is input normalization. You can see on this one, the mouse and the elephant are about the same size, and that's kind of what normalization does. There's several methods we can use to solve the problem of size difference, and we'll be looking at that next time. So if you enjoyed it, please subscribe. If you've already subscribed, thank you so much, and have a great holiday. I will talk with you soon. Peace.